Welcome to Math TV with Professor V. In this video, we're going to look at how to compute volumes for solids of revolution using cylindrical shells, or the shell method. Now, there's two main techniques when we're finding volumes for solids of revolution, and that's either discs or washers, which we learned previously. And in this video, we're going to talk about the shell method. The big difference between the two is the direction that you are peeling or slicing in relationship to the axis of revolution. So in the previous technique, discs and washers, not what we're going to learn in this video, we sliced perpendicular to the axis of rotation. Meaning, if you spun around a vertical line, say for example the y-axis, and we were in the previous lesson, we took slices perpendicular to that axis, slices moving up and down, so we would integrate with respect to y. And we'd either have a disc or a washer. And then similarly, if we spun around a horizontal line like the x-axis, we took slices, again, perpendicular to the axis of rotation, and we would integrate with respect to x. In this method, we're going to be peeling cylindrical shells parallel to the axis of rotation. So here's the thing to keep in mind. When using discs and washers, if you would have integrated with respect to x, then that means if you're doing cylindrical shells, you'll integrate with respect to y, and vice versa. If doing discs and washers, you would have integrated with respect to y, then in this section for cylindrical shells, you would integrate with respect to x. They are perpendicular to one another, okay? Opposite variables. So what exactly is a cylindrical shell? What the heck is going on here? So we still start with an area, a region in the XY plane. We spin it around an axis. So that they have to tell us, hey, you're going to spin around the x-axis or you're going to spin around the y-axis. So say, for example, I have here y as a function of x bounded between a and b. This is just arbitrary example, and we're spinning it around the y-axis, okay? Instead of slicing perpendicular to the axis of revolution, in order to compute the volume of this three-dimensional solid, what we're going to do is peel parallel to the axis of rotation. So you can think of it as like from the outside in, kind of like how you peel one of those. Have you seen one of those sticky lint rollers where you just take layer by layer off? Yes, so think of this as like little sheets of the lint roller, or kind of like an onion, but I don't feel like an onion peels nicely. People say that all the time, but I don't know, whatever. Layer by layer. Layer by layer. And if you look, what are each of these layers that we're peeling or we're unrolling from the solid? It's a cylindrical shell. It's a cylinder, okay? And just like in the previous method when we did discs and washers, if you sum up a bunch of areas, that will give you the volume of the solid. So we need to sum up the area of each of these cylindrical shells. Well, if we unroll them, they are basically rectangles, right? Rectangles whose height is given by the function f of x. And then the other side, when you unroll it, is the circumference. So that would be 2 pi times the radius. That's how we normally compute the area of a cylinder. But in this case, the radius is always going to be x if we're spinning around a vertical line. See, one cylindrical shell right here, its radius is wherever I chose to take this x value. The next one is wherever I chose to take this x value, so on and so forth. So the radius of each cylindrical shell basically goes from the axis of rotation to the outer edge of that shell, of that cylinder. And in this case, it's just going to be marked by where I choose to take x, where I choose to peel, okay? The function that bounds the region, that helps determine the height of each cylindrical shell, but not the radius. This is key. The function is involved with determining the height, not the radius. The radius only has to do with, in this case, x, wherever we choose to peel a cylindrical shell. Why am I making such a big deal about this? Because a lot of the times when students are identifying the radius and the height, they get them a little jumbled up, okay? So circumference, this is 2 pi times r. Let me label that that's r. And then the height right there, the height right there is given by the function. That already says h, so that's good. Let's make a skinnier r. There we go. All right, now you can see here we have a visual. Here's the cylindrical shell, and if it's unrolled, here's 2 pi r, which is 2 pi x, and then the height is given by f of x, okay? So basically, you don't need to draw this unrolled version of the cylindrical shell when you're setting up each problem. You're just going to draw one typical one in the 3D diagram, and I'll show you how to do that in all the examples that we work through, but you just need to remember the formula that you're working with. So it could be either, you have two options, 2 pi a to b r times h dx, or it's going to be 2 pi, if we're integrating with respect to y, c to d r times h dy. And just keep in mind, r, if we're integrating with respect to x, will only have an x in it, or maybe a constant, plus or minus. The function that bounds the region is expressed in the height, never the radius, okay? The function that bounds the region is expressed in the height, not the radius. The radius is just going to be plain old x or plain old y, maybe plus, minus, some constant, but not the function. Got it? Fabulous. Okay, let's try some examples, right? Okay. We'll start off relaxing, meaning the region will already be graphed. That way we cannot be so traumatized by having to graph whilst doing these integrals. So use the shell method to find the volume of the solid generated by revolving the shaded region about the indicated axis. Now, even if the directions don't specify, I'm going to list for you key components that have to be included in any problem that you do like this to be considered thorough, full credit, all that good stuff. So graph of the region, okay, which they already gave us, so that's nice. Graph of the resulting solid after spinning. And then in the previous lesson, we drew a typical disc or washer. This time we're going to draw a typical shell and label the radius and height, okay? Those go without saying. All right, I'm glad we're having an agreement on this. Now, here we go. Shell method. We're going to do only shell method this lesson. Spinning around the y-axis. So that means we're spinning this way. Okay, so I'm going to just basically reflect the region. That was not fabulous. Hold on. Okay, that's a wee bit better. I reflected the region, and it's a solid, right? So you can add more dimension if you like to your picture. Just don't let it get cloudy. So graph of the region, check. Graph of the solid, check. Typical shell. This is always difficult for students. So here we go. I'll show you my foolproof method. If you spun around a vertical line, and it's time to draw a typical shell, vertical line, draw a baby vertical line segment in the original region. So here we go. We spun around a vertical line. Here's another little vertical line. I would like it a little chunkier. Okay. Oh, there we go. And then you're going to reflect that onto the other side. That's the height of your cylinder. Now, connect the two, draw the base and the top, and there's our cylindrical shell. Okay? Make sure this height stays within the shaded region. None of this wildness going out here into the empty space. Remember, we sum up the areas of these cylindrical shells. That way we can get the volume of this solid. So it would make no sense if they were to go outside into the open space. Then they would not be helping us compute the volume of what we have going on right here. Yes? Okay. So, like I said, that little baby vertical line segment, that was the height. And then this right here, from the axis of revolution to the outer edge, that is your radius. So let's identify what those are before we set up our integral. Okay, great. Now, the radius will only involve, in this particular case, either x or y. How do we know what we're integrating with respect to? Well, look here. If we're spinning around the y-axis goes this way. Then I peel, or I make cylindrical shells parallel to the axis of revolution. So I would peel, I'm only going to draw one shell for the problem, but you could draw more. You could draw another one over here. Here's another cylindrical shell, etc. And you can see that they are getting layered, or they're moving. Oh, come back. In the X direction. Can you see that? There's another one. Okay, it's getting messy. I'm going to erase it. But you could see what's changing. This radius is changing with respect to X. Yeah? The height's also changing because the X value is changing, so the function's changing. But I'm stacking, or I'm peeling them in the X direction. Here's one, here's one, here's one. Which way am I peeling? Look at the way I'm moving. It's in the X direction. So I'm going to integrate with respect to X. Let's write that down. Integrate with respect to X. Another way, if you're just horribly confused, you can say, okay, I'm spinning around the y-axis. If I was in the previous lesson, I would have sliced perpendicular and integrated with respect to y. So since we're doing shells the other way, then I'm going to integrate with respect to x. That works for some people. Not my favorite thing to say, but you know what? Whatever works for you. It's not like this is easy stuff. What did I tell my class the other day? I said no one comes out of the womb computing volumes via cylindrical shells, but some people make it look so effortless. You should see my mother. She's the queen of this. It just comes from so much practice, right? Some people are naturally better than others, but really you just practice it enough, you too can be fabulous at this. You can do it. Okay, so now after all that, radius in terms of x, height in terms of x. Here's the radius from here to here, okay? From where we're spinning to the outer edge. Again, I want you to think back to when you computed areas between curves just a few sections ago. Right minus left boundary. On the right is just x. We're spinning around the y-axis, which is x equals 0. So the radius is just x. I'm going to write x minus 0, which is x. It's going to get spicier later, okay? What about the height? Now the height will involve the function that bounds the region. Top minus bottom. What's bounding the height on the top? This function right here, 4 sine x over x. What's bounding the height on the bottom? Y equals 0. So this is 4 sine x over x minus 0, which is just 4 sine x over x. And then look, it's our lucky day. They already gave us that the region's bounded from 0 to pi, so we're ready to set up our integral. And it's in terms of x, so that's already a big clue. We should probably integrate with respect to x if you were just totally lost. Okay, so volume is 2 pi. Put the 2 pi outside, you know. Limits are from 0 to pi. And then we have radius, which is x, times height, 4 sine x over x dx. Good? Well, it's our lucky day. These x's cancel. And then I'm just left with 2 pi integral 0 to pi 4 sine x dx. All right, very good. Very, very good. Now, if you want, you could take the 4 out. So you could have 8 pi times integral 0 to pi sine x dx. And then from here, let's just think, whose derivative did we take to get sine x? Not cosine, because derivative of cosine x is negative sine x. So this is 8 pi times negative cosine x evaluated from 0 to pi. Okay, good. And then let's just take the negative out. Negative 8 pi times cosine of pi minus cosine of 0, which is 8 pi times cosine of pi is negative 1 minus cosine of 0 is 1. And we have that negative out there, don't forget it. Negative 8 pi times negative 2 is positive 16 pi. You should not get any negative answers when doing these problems because these are volumes. For solids of revolution, they won't be negative, okay? When you move on to calculus 3 later, you'll do some like net volumes, and those can come out negative, but that's a whole different beast. Don't worry about it. So just keep in mind now, if anything comes out negative, you messed up somewhere, okay? All right, so that was a good warm-up example. Let's turn the heat up, move on to something else. Use the shell method again to find the volume of the solid generated by revolving the shaded region about, in this case, the x-axis. Oh, how fabulous. Okay, we're spinning around the x-axis. That means we are spinning this way. What's the region gonna look like? Just basically reflect it, you know? Something like this, something like this. Keep it going. Okay. We're spinning around the x-axis. If you want to add a little dimension, feel free. And let's decide which way we're going to integrate. So if we're spinning this way, we're going to peel parallel to the axis of revolution. So I'm going to peel here, peel here, peel here, this way. So we're integrating with respect to y. Okay, let's draw a typical shell. That is key. So start in the original region. If I spun around the x-axis, that's a horizontal line. So draw a baby horizontal line segment in the original region, right here. Reflect it on the other side. That's the height of your cylinder. Now connect them, make a cylinder, and there you go. So that's the height, and then the radius is right there. Can we identify what they are in terms of y? Okay, so the radius goes from where you're spinning to the edge here. Remember, it will not involve the function. It's just, if we're integrating with respect to y, we're just peeling, or the radius is increasing as y increases. So don't get all fancy schmancy. Top minus bottom instead of right minus left this time, because see how they're stacked? Top is y, bottom is 0. So radius is just y. Y minus 0, which is y. Now the height, a little more spicy. Here's the height of a cylindrical shell. This time we're going to do right minus left because of the way it's stacked. What's bounding the height on the right? That's x equals 2. What's bounding it on the left? This curve. Why right minus left? That's always the order in order to get a positive quantity, right? Bigger minus smaller is going to be right minus left, or top minus bottom. If you go the other way around, left minus right, that makes no sense because it'll come out negative, okay? Right is x equals 2, this line. Left, the curve. So that's the height. 2 minus rad 4 minus y squared. Okay, that's it, literally. Limits of integration, if we're integrating with respect to y, have to be in terms of y. And the limits are determined, pay attention to what I'm going to say right now, by the original region before you spun it. Why do I say that? Because the limits are going to go from 0 to 2 for the original region before I spun. They should not go from -2 to 2. That's too much before you spin, okay? I see a lot of mistakes from that. Okay, that's why I'm being so serious. V equals 2 pi integral 0 to 2. Radius is y times the height, 2 minus rad 4 minus y squared dy. Okay, now we just got to integrate our little hearts out. So let us distribute this y, 2 pi 0 to 2. This is 2y minus y times rad 4 minus y squared dy. The dy is too close and I need parentheses right here first. Okay, so let's think about what we're going to do. We can do antiderivative of 2y in our sleep. That's no problem. What about this guy? It's going to need a u sub, right? You're going to let u be 4 minus y squared, and then this will be part of my du. I know that because anytime you have something that's 1 degree lower than the quantity underneath the radical or in the parentheses, then u sub will help us out. But this doesn't need a u sub. So what you need to do is just split the integral, okay? When you get more advanced, you could probably do this U sub in your head, but I don't want to traumatize you, so we won't even talk about such things. So we'll split these guys up, okay? The band is breaking up. 0 to 2, 2y dy. Let's just do the, you know what? Let's just do the 2 pi to everybody later like this. Yep. 2 pi times that one minus integral 0 to 2 y rad 4 minus y squared dy. Like that, okay? Very good. So this is integral 1, this is integral 2, and then at the end I'll multiply everybody by 2 pi, okay? So integral number 1, we have 0 to 2, 2y dy. Antiderivative of 2y is just going to be y squared, and the 2 cancels out, so that's nice. And we evaluate that from 0 to 2, so that's 2 squared minus 0 squared, so that's just 4. That one's done. That was pretty relaxing. Integral number 2, 0 to 2 y times the square root of 4 minus y squared dy. So like I said, we're going to let u be 4 minus y squared. Then du would be, derivative of 4 is 0. This is going to be negative 2y dy. That's sort of what I have. I just have y dy. So that means negative 1/2 du is y dy. Okay, so we've got a negative 1/2 on the outside, rad u du, and then let's compute our new limits of integration, okay? So take these, plug them in for y, and figure out what they are in terms of u. So u of 0 would be 4 minus 0 squared, so 4. And then the upper limit, u of 2, would be 4 minus 2 squared, which is 0. Whew, okay. Now everything's rewritten in terms of u. You know what I'm going to do immediately? Get rid of this negative by flipping the limits of integration. I highly recommend doing that. Plus, it's better when 0 is the lower limit, you know. 0 to 4, and then I'm going to rewrite this as u to the 1/2 du, because I'm getting ready to take its antiderivative. Okay, good. So what's the rule? We add 1 to the exponent, divide by the new exponent. So we'll have u to the 3/2 with a 2/3 in front, evaluated from 0 to 4. No more du, no more integral sign. I'm running out of space. Who knew? Because I didn't do the shortcut. I know. I'll show you the shortcut in a hot sec if you want to see. Okay, cancel, cancel. And then this is going to be 1/3. Leave the 1/3 out. 4 to the 3/2 minus 0 to the 3/2. 4 to the 3/2, don't you dare grab your calculator. This is going to be the square root of 4, which is 2. Then you raise it to the 3rd power, that's 8. So 1/3 times 8 is 8/3. That's the result from integral number 2. Okay, see, nothing traumatizing. So altogether we have 4 minus 8/3 times 2 pi. So we have, summary time, 2 pi times 4 minus 8/3. 4 we know is 12/3, minus 8/3 is 4/3, times 2 pi would be 8 pi over 3. That's our final answer, okay? What was I saying about the shortcut? If you're just starting Calc 2, it probably won't feel nice, but by the end of the semester, or maybe even partway through, say you were at this point, 0 to 2, 2y minus y rad 4 minus y squared dy. You could probably do it all in your head. So you would do 2 pi, antiderivative of 2y you would know is y squared. And then basically just in your mind, you would say, if I let u be 4 minus y squared, right? If I let u be 4 minus y squared, you would get to the point where you saw, oh, we would just have a negative 1/2 du, right? Equals y dy, which means you need to just compensate or add an extra negative 1/2 when you take the antiderivative of this term. And so then you would just add that in there. You would say, oh, I've got minus negative 1/2. Leave this stuff alone. It's currently to the 1/2 power. Add 1, divide by that exponent, and then you're done. And then you just go from 0 to 2. Okay, that might seem a little aggressive, but with enough practice, when you do enough of these u-subs, it'll feel very natural, okay? No aggression, just great. So I don't mind if you're in my class, if you can see all those steps in your head and you just want to skip the u-sub, that's not a problem. Okay, let's move on to another example here. So the next example says, use the shell method to find the volume of the solid generated by revolving the region bounded by the given curves and lines about the y-axis. So that's where we're spinning, about the y-axis. You must include a clearly labeled sketch of the region, amongst other things. Yes, of course. So we have y equals 4x squared and y equals 4 rad x. So you should just have a general idea. 4x squared, parabola opening upward. 4 rad x is just square root function stretched. So let's go ahead and find their intersection. That should always be your first move, okay? So let's find the intersection for the two curves, then we can draw the region, then we'll worry about spinning it, then we'll worry about the shell. But this is step 1. So let's set 4x squared equal to 4 rad x. How to solve? Just, divide by 4 on both sides. Now you've got x squared equals rad x. And then, most students have a panic attack. Let's just square both sides. We do run the risk of extraneous solutions, but that's fine. We can check them both in a second. So we'll have x to the 4th is equal to x. No, we don't divide by a variable. Super illegal. The math police will come for you. Set it equal to 0. X to the 4th minus x equals 0. I can factor out an x, and I have x cubed minus 1 is 0, which means x is 0 is one point where they intersect. X cubed equals 1, which would be at x equals 1. Okay, and then I can just confirm by looking, that nothing's extraneous. Both of these are points of intersection. So they intersect at 0, 0, as well as at 1, 4. Yes? Fabulous. And we're spinning around the y-axis. So I'm just going to draw my graph using quadrants 1 and 2. Nothing's happening in quadrant 3 or 4. So they don't need to be there. Here's x, here's y. I'm going to say this is 1. And then we're going to scale up to y equals 4. Scale how you wish, do what feels right. So let me draw the parabola. It's going to go through 0, 0, 1, 4, something like this. This is 4x squared. And then 4 rad x, I know between 0 and 1, it's going to lie up above the parabola like this. If you're not sure which graph is above or below, then plug in something like a half, and then you can compare the y values. But I know by the shape of these curves, right? Oh, I did not mean to move that whole thing. Anyways, I knew by the shape of these curves that if rad x is going to intersect, it's going to be like this. So that's basically where the 1, 4 and the 0, 0 are, So this is the region that we're going to spin right here. Let me shade it in. And we're spinning this around the y-axis, okay? So if we're spinning around the y-axis and we're peeling parallel to the axis of revolution, right? You're spinning this way, we're peeling this way, we're going to integrate with respect to x. Integrate with respect to x. All right, let me draw what the region's going to look like on the other side so we can kind of get our solid going. Yes? Something like this. I don't shade the reflected part as thoroughly as the original because it helps me remind myself this is what I'm going to use to determine the radius, the height, as well as the limits of integration. Don't shade in the reflected part too much so that you forget which one the original one was. Okay, now let's draw a most fabulous cylindrical shell. If you're spinning around a vertical line, then draw a vertical line segment in the original shaded region. You can draw it anywhere. You can draw it here, 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 wherever your heart desires, okay? I'm gonna draw one right here. Don't go outside of the shaded region. No, no, no. Reflect it on the other side. That's the height of your cylindrical shell. And then now, just add a little dimension. And there you go. Here is the height. Where's the radius? It's right there. That's the radius. Okay, let's figure out what they are in terms of x. Radius will not involve any of the functions that bound the region. If we're integrating with respect to x, the radius is just going to be right minus left. In this case, x minus 0. So that's it. X minus 0 or x. Now the height, let's look here. Here's the height. Now we can use the functions. Top minus bottom. Top minus bottom. Which function's on the top? 4 rad x. Which one's on the bottom? 4x squared. This is why we did that whole section on area between curves before these volumes, because you have to do the same idea. Top minus bottom, right minus left. Okay, so volume is going to be 2 pi integral. Limits are going to be limits for x on the original region before we spun. So from 0 to 1. Not anymore. Don't you dare look over there and think you have to go from -1 to 1. Original region only. Then we have 4 rad x minus 4x squared times x dx. All right, now I'm going to show you some tips on how to integrate more swiftly. I can factor the 4 out, so then I'm going to have 8 pi outside my integral. Do that. And then remember, this is x to the 1/2 power, and we're going to distribute this x now to both of these terms inside. So x to the 1/2 times x, add the exponents, you'll have x to the 3/2 power minus, this is going to be x cubed dx. Not bad, right? Love it. Keep the 8 pi outside, minding its own business. Now, add 1 to the exponent, divide by the new exponent. So we'll have x to the 5/2, very good, with the 2/5 out front, minus, same thing, add 1, divide by the new exponent, 1/4 x to the 4th. And this is all evaluated from 0 to 1. Thank goodness, you know. Whew. And then we have 8 pi times 2/5 times 1 to anything is 1 minus 1/4 times 1 minus, and then yeah, if I plug in 0 for the lower limit, everything's 0. So we've got 8 pi times 2/5 minus 1/4. Let me show you my little multiplication shortcut with the fractions, or subtraction shortcut. You do 2 times 4, that's 8, minus 1 times 5, that's 5, over 20. That's 3 over 20 times 8 pi. 8 pi times 3 over 20. I can cancel out a 4, right? This is 5, and now this is 2. Final answer, 6 pi over 5. That was lovely. Should I put that on the exam this semester? I don't know. Kind of liking it. Vote down below. Okay. I have a few more, don't worry. Use the shell method. Again, same directions. We're spinning around the y-axis. So if we're spinning around the y-axis and we're doing the shell method, we're going to integrate with respect to x. Very good. We're integrating with respect to x. I have a question. If I switched it and said we're going to use discs or washers, then you would integrate with respect to y, okay? It'll always be the opposite variable if you switch the method. One's for parallel to the axis of revolution, that's what we're doing now. Other method is for perpendicular to the axis of revolution. Okay, let's see. 6 over x. Do you know what 1 over x looks like? This guy, right? Okay. Y equals 0. We know where that is. Ba-boom. X equals 7, X equals 9. So we've got two vertical lines and the x-axis bounding a region along with 6 over x. So I'm really only going to pay attention to the first quadrant, right? We don't need much else. You can find the intersection, but it's really not so necessary. Okay, I'll show you why. So let's just draw, and if we're spinning around the y-axis, then let me put quadrant 1 and leave space for quadrant 2 as well. Okay. X, Y. There's a vertical asymptote here, right? Okay. And that's also what we're spinning around. And then the vertical lines, x equals 7 and 9, bound the region. So here's what we'll do. We'll say this is x equals 7, and then this is x equals 9. Here's these two vertical lines. And I'm just going to make up, because if it's y equals 6 over x, this is 6 over 7, and then this is 6 over 9, which is 2/3. And then just connect it. It's going down like that, okay? And then there's more to the graph like this, 6 over x, but I'm not interested in that, so I'm not even going to draw it. And then y equals 0, that's right here, that also bounds the region. So this right here, this is 6 over x, and then we've got the two vertical lines. So here we can shade in the region, and that's really all we need, okay? And then we're spinning around the y-axis, okay? So let me just reflect all of this over here. It's gonna look something like this. Swoop down, here you go. That's the reflected region. And then you can add some dimension, should you wish to, okay? It's like this. Okay, so now let's draw a typical shell. If you spun around a vertical line, draw a baby vertical line segment in the original region. Here it is, baby vertical line segment. Reflect it. That's the height of your cylindrical shell. Now connect it, make a cylinder. Very nice. Wow, we're getting so good. Here's the height. Here is the radius. Okay. Let's see if we can identify them in terms of x. Radius again, right minus left. This is whatever x is minus, we're just spinning around x equals 0. So it's just x minus 0 or x. What about the height? Top minus bottom. 6 over x minus, this is y equals 0. So just 6 over x. I'm going to put the minus 0 though. That way you just remember to always think top minus bottom or right minus left. Just get in that habit. And then the limits of integration are for the original region in terms of x, 7 to 9. 7 to 9. Okay, so volume equals 2 pi, limits from 7 to 9. You should always read it lower limit to upper limit. You don't say from 9 to 7. That makes no sense. From 7 to 9. It is a pet peeve of mine. I don't know, and it's been making me more angry this semester than usual. X times 6 over x. Cancel, cancel. Oh my, what a cute little integral. 2 pi, 7 to 9, 60x. Antiderivative of a constant, you just slap an x on it from 7 to 9. This is 12 pi, 9 minus 7, that's 2. So altogether, this is 24 pi, and we are done. Voila. That was not bad, right? The one before was spicier. Okay, I do have a few more. Can you tell? Use the shell method to find the volume of the solid generated by revolving the region bounded by the given curves and lines about the x-axis. So here we have x equals 18 minus y squared. That's a parabola opening to the left. How do I know to the left? Because of the minus in front of the y squared. and it's been shifted 18 units to the right. And then x equals y squared, that opens in the positive direction to the right. So the region is going to be something like this, you know? And this time we're spinning around the x-axis. So if we're doing the shell method and spinning around the x-axis, we're spinning around a horizontal line and we peel cylindrical shells parallel to that axis, then that means we're going to integrate with respect to y. Okay, so first things first, we have to find the intersection of these two curves. That's crucial. Otherwise, you can't draw an appropriate graph and you wouldn't know what the limits of integration are. Don't just make a table. You'll sometimes waste precious time and you may not find the point of intersection, especially if it's a fraction or an irrational number. So that's just silly. So 18 equals 2y squared. Y squared is 9. Y equals plus or minus 3. Okay, that's good to know. And let's see, if y is 3, then x is going to be 9. So the graph those two curves intersect each other at 9 plus or minus 3. But then I'm also noticing that y equals 0, which is the x-axis, bounds the region that we're spinning. So let's just take, in this case, we just need 1/2 of it. We'll just take the top half and spin the top half. You could either spin the bottom half or the top half, it won't matter, but we're not spinning the whole thing. So I'm just going to use the positive 9 plus 3 for the intersection of the two curves. Okay? Good. So let's graph what's going on. Again, you could choose to spin either the bottom half or the top half. It's just that since y equals 0 is bounding it, you're not spinning the whole region. I know I need 9, 3 on there, and then 18, and then 1, 2, this is 3. Okay. So they intersect here. And so this is the part that's like not really crucial. This is x equals y squared. And then 18 minus y squared, if you plug in 0 for y, x would be 18, right? On this curve, 18 comma 0, that's the vertex. And then it's intersecting the other curve at 9, 3, so something like that. And then there's more here that's not interesting for us. And also, don't forget y equals 0 bounds the region right here. So I'm just going to choose the top half. You could also have chosen the bottom half. It really doesn't matter. And we're just spinning all of this around x equals 0. So when we spin it, then the solid's going to reflect. This region's going to reflect. Yes? Good. Okay. And be somewhere over here as well. Okay, so it's looking like a little weird shaped football of sorts. And now we have to draw a typical cylindrical shell. So if we're spinning around a horizontal line, go to the original region and draw a little baby horizontal line segment that lives within the region. Don't go out of bounds. That's a big no-no. Okay, there it is. Now you reflect it on the other side. That's the height of your cylinder. And then draw the rest of the cylinder. It should be in the solid, not floating outside. So here's the radius. Here's the height. Let's see if we can describe them in terms of y this time. The radius will not involve the functions that bound the region. It's just going to involve y. Yes? So here's the radius. From where we're revolving to the outer edge of the cylinder, top minus bottom, y minus 0. So radius is just going to be y minus 0, which is y. Then look at the height here. Right curve minus left curve. Who is this bounding it on the right? Oh, I didn't fill it in. Shame on me. It's 18 minus y squared. Right minus left, 18 minus y squared minus y squared. So this is 18 minus 2y squared. Good? Limits of integration are going to be in terms of y, what bounds the original region from 0 to 3. OG region only, pre-spin, volume equals 2 pi integral 0 to 3 radius times height dy. Okay, this one's probably one of the most relaxing ones we've done also. 0 to 3, this is 18y minus 2y cubed, and then we can just go term by term. Antiderivative of 18y is going to be 9y squared minus, I'll have y to the 4th divided by 4, so now we have a 1/2 y to the 4th from 0 to 3. So this is 2 pi times 9 times 3 squared is 9, minus 1/2 times 3 to the 4th is 81. If I put 0 for the lower limit, everybody's 0. So this is 2 pi times 81 minus 81 halves, which is 81 halves in here, times 2 pi, the 2's cancel, so I just have 81 pi for my final answer. Nice. Okay, how are we doing? You know, I'm just trying to give you enough examples so that you can feel like you have this in the bag, that even on a bad day, you can do cylindrical shells, no problem. Become a pro. I think I have like 3 more. Does that feel excessive or does that feel fabulous? Use the shell method to find the volume of the solid generated by revolving the region bounded by the given curves about the given lines. So we have y equals 5x. We know what that looks like, right? Positive slope. Y equals 0, and then x equals 2. So we've got this triangle, and we're spinning around x equals -3, which would be over here. So that's my sloppy start of a graph. Let's put it all together properly. If I'm spinning around x equals -3, then I need a lot of quadrant 2, right? Okay, good. And then y equals 5x, that's no big deal. This is 5x. If it's going to hit at x equals 2, that would be at 2, 10, right? Good. I think probably one of the hardest parts about this lesson for the majority of students, at least the ones that I see, is that their graphing skills are just not strong, you know. And there's a lot of reasons for that. It's not always your fault if you're not good at graphing. A lot of students just don't like it, but I think they don't like it because they're just not comfortable with it. If you can get good at graphing, it will make life a lot better. 10, 1, 2, 3. If you need to review graphing, I'll link here the pre-calculus video that I have on just like basic functions. And then if you want to delve deeper into the pre-calc video lecture playlist, I have a bunch on just like graphing with transformations and stuff if you need to brush up on your parent functions. That could be helpful. So y equals 5x. Going to go through here. Okay. And then x equals 2 bounds the region. There it is. And then y equals 0 also bounds the region. So that's down here, yeah? Good. So then we've got this little triangle. So cute. Look at this little triangle. I love this little triangle. Shade it in. Have fun. Make the graphing fun. Don't hate your life. And then we're spinning around x equals -3. Okay. So if we're spinning around a vertical line and we're going to peel parallel to the axis of revolution, which way are these peels moving? They're moving in the x direction. So we will be integrating with respect to x because we're doing shells. So let me see, this is about 3 units, right, from where we're spinning. So 3 units from where we're spinning on the other side, I'm going to draw like the mirror image. Something like this. And I'm not going to shade it in completely because I still want to remember what the original region was. So it's looking something like this. Here's the top of it. Voila. Okay, time for a typical cylindrical shell. You go to the original region. You say, I spun around a vertical line, so I'm going to draw a baby vertical line segment in the original region, and I'm not going out of bounds. I'm going to reflect it on the other side. That's the height. Let's remind ourselves if you need to. This is the height. And then connect it, and there's our cylindrical shell. Here's the radius. Wow. Wow, wow, wow. Okay. Radius and height. Let's figure out what they are in terms of x. For the radius, be careful. This is a little different. We're going to do, this is where we were spinning, right? X equals -3. Right minus left. This is x minus -3. So radius is x minus -3, which ends up being x plus 3. I'll say it again. Here's the radius. Right minus left. Do you want me to shade in the radius? Like, here's the radius. That piece right there. There's the radius. Right minus left. X minus -3. So it's x plus 3. Height. Height is right here. Top minus bottom. What's that? 5x minus 0. So just 5x. Good? Limits of integration are in terms of x that bound the original region. That's just from 0 to 2. There's nothing over here, so only go from 0 to 2. Okay, we're ready. Volume equals 2 pi integral 0 to 2 x plus 3 times 5x dx. Take the 5 outside if you like. Then I have 10 pi integral 0 to 2. I'm going to distribute the x squared plus 3x dx. All right, then we have here 10 pi. This will be 1/3 x cubed plus 3/2 x squared, evaluated from 0 to 2. 10 pi times, plug in 2. 2 cubed is 8, so we have 8/3 plus 3/2 times 4 minus 0, right? Lower limit 0. So what is that? 10 pi times, this is 8/3 plus 3/2 times 4, that's 6. 6 is 18/3. Yes. So 8 plus 18, that's going to be 26/3 times 10 pi, 260 pi over 3. That one's done. Are you feeling professional? Yes? Could you write your own exam? I mean, it's not hard to write an exam. It's harder to take an exam. Think about it. Okay, I think I have two more cute little ones. Oh, yeah. Find the volume of the solid generated by revolving the region about the given axis. What's the given axis? This time we're spinning about the line y equals 1. Use the shell or washer method. So just to practice, we're going to do shells. If you want to redo this with the washer method, knock yourself out. Okay? This should kind of remind you of one that we've already done, a little bit similar. X equals 3 rad y. Think about it. That's just half of a parabola. I'm not gonna solve for y in terms of x, but I just want you to see how I knew that, because x over 3 equals rad y. If I square both sides, then I have x squared over 9 equals y. So if I have y equals x squared, that's a parabola. Since I only have half of it though, right, the positive radical, then we're just going to be on the right half, okay? So it's just going to be like that piece. And then x equals -3y, that's just a line, negative slope, cutting through. And then also the line y equals 1 bounds the region, and we're spinning around y equals 1. Okay, so let's go ahead and find the intersection. That's the first thing. I'll just erase this. That was just me kind of getting prepped for what's to come. Okay, so 3 rad y equals -3y. This is me finding the intersection. Again, we've seen something similar to this. You can just divide by 3 on both sides. So we have rad y equals negative y. Square both sides, which means y equals y squared. So y squared minus y is 0. Factor out a y. And we get that they intersect at either y equals 0 or y equals 1. Now, one of these might be extraneous. If you forgot from algebra, anytime you square both sides of an equation, you lose information. So you run the risk that one of these is an extraneous or extra solution that only satisfies the squared equation, not the original. So you just check, that's all. 0. 0 works, but 1 does not, because square root of 1 is positive 1, but negative 1 is not equal. So I'm junking this one. Here's the extraneous little dude. So y equals 0 is the only place that they intersect. Huh. Okay, whatever. We can deal with it. And we're spinning around y equals 1. Okay. So I'm just going to draw a lot of quadrant 1 and 2. Okay. And since y equals 1 does bound the region, let's figure out when y is 1, x would be negative 3, so negative 3, 1, and then this would be positive 3, 1. So I'm just going to go out to 3 and negative 3 in the x direction. And then here's y equals 1. Okay? Okay, so this line bounds the region. X equals 3 rad y. Draw your half a parabola. It's also going to go through 0, 0. So here's x equals 3 rad y. And then the other one's just line, so just connect it straight. This is x equals negative 3y. So here's the region. Okay. The region has to be enclosed by the given curves. And then we're spinning around y equals 1. Okay, so we're spinning around this very line right here. Okay. So it's going to reflect something like that. And we have more over here. Okay, if we're spinning around a horizontal line, okay, so we're spinning around a horizontal line, I'm going to peel parallel to the axis of revolution. So these peels are moving in the y direction. So I'm going to integrate with respect to y. Since I'm doing shells, if I were to do washers, you would integrate with respect to x. It would just be a disc. There's no hole in the middle. It wouldn't even be a washer. But anyways, who cares? We're not doing it right now. Okay, so let's draw a typical shell. If you spin around a horizontal line, then go to the original region, draw a little horizontal line segment, wherever your heart desires. Right here feels like a nice place. And then I'm going to reflect it on the other side. That is the height of my cylinder. That's the height. Now draw the rest. There we go. Beautiful. There's your radius right here. There's your radius. Okay. Are we all right? Okay, let's figure out what they are in terms of y. Radius and height. Let's do the radius first. Radius. Go from the center to the edge, top minus bottom. Who's this? That's y equals 1. Minus, no, you don't use the function for the radius, only x or y. In this case, we're integrating with respect to y, so it's just going to be 1 minus y. Height. Here's the height, right minus left. Right minus left. 3 rad y minus negative 3y. So 3 rad y plus 3y. Good? Limits are for y that bound the original region before we spun. So go from 0 to 1. That's it, just 0 to 1. Okay, volume equals 2 pi integral 0 to 1 radius times height. Good? You know what I want to do immediately? I want to factor this 3 out. And then I'll have 6 pi times the integral 0 to 1, 1 minus y times, rad y is y to the 1/2 plus y dy. And I'm going to FOIL all this out now, but it'll be a little bit nicer to do. So 6 pi integral 0 to 1, this is y to the 1/2 plus y minus y to the 3/2 minus y squared. Good? Okay, then from here we just anti-differentiate term by term. So this will be 2/3 y to the 3/2 plus 1/2 y squared minus 2/5 y to the 3/2 minus 1/3 y cubed from 0 to 1. Thank goodness, just 0 to 1, huh? And then 6 pi. If I plug in 1, everything's just going to be a 1. So 2/3 plus 1/2 minus 2/5 minus 1/3 minus 0 for the lower limit. And what's my common denominator? 15. So 6 pi times, if I multiply that by 5, that's 10. No, not 15. Heavens to Betsy. This 1/2 means my common denominator is 30. Yeah, 30. Okay, so times 10. 20 plus 15 minus 12 minus 10 over 30. Let's see, that's going to be 10 plus 3, 13 over 30. 6 pi times 13 over 30, cancel. This is 5, so just 13 pi over 5, okay? There we go. Only one more for you. Are you sad? Our time together is nearly coming to a close. Okay. Oh, just kidding, I lied. That was it. That was the end. All right. You know which one I was thinking to do if you're in my class? Number 30 on the practice test, but I just did it in class the other day and it's so similar to this one and they already gave you the graph, so we're good. We're good. Hopefully this video helped you tremendously. I have to give credit where credit is due because to identify the radius and the height, I kept telling you right minus left, top minus bottom, all that stuff, that is game changing. I did not come up with this explanation technique. That is all thanks to my mother, the queen. So she is also a community college math professor, in case you didn't know. I did a little video interviewing her, sort of. I'll link it here if you haven't seen it yet. But she is my biggest inspiration, and I turn to her when I need advice and help, and she's taught me so much. But hopefully I can share and impart everything she's taught me with you guys as well. Share this video, give it a thumbs up, subscribe if you haven't already. It would mean so much to me. Leave me a comment down below. What was your favorite part? Was it spicy? Do you hate shells? Do you like washers better? What are you doing the rest of the day? I'm going to go to ballet right now, and I'll see you guys all soon. Take care. Bye-bye.